The second part of section 3.2 is the mean value theorem, often also just called the MVT. So we often abbreviate these theorems. So the MVT. To use the MVT, you need to have a function that is continuous, and you need to have a function that's differentiable. Now, if you have that, what the mean value theorem says is that there is some value on the interval for which the derivative, not that it's equal to 0, that's Rolle's theorem because that's a specific case, but that f of b minus f of a over b minus a is equal to the derivative at c. So I'm going to do the best I can with my tablet here, but the idea is there is some c, and I'm going to draw, the best I can with my tablet here, tangent line at c. And then notice here we have b and we have a, so we have f of b and f of a. And if I draw the secant line between them, again, the best I can do here, what I want you to see is that the slopes of those two lines are the same. That's the idea behind the mean value theorem. It says that there will be some place where the slope of the secant line between the two endpoints is the same as the slope at some other point from the tangent line, the slope of that tangent line. So some c exists so that that is true. And that's essentially the big idea behind the mean value theorem. So we're going to take a look at where we might see this. So I have the graph of this over on this side, and what I want you to see is, this is obviously better than what I can do on my tablet, the reddish function is the f of x equaling x cubed plus x minus 1. Now the green line is the secant line, so it's the line between 0 and 2, so the points 0 and 2, the x values. And then what I want you to see is that there's some value here, this is some c right here, for which you can see that the slope of that line, that tangent line there, is the same as the green line. So the blue line and the green line have the same slopes. And the mean value theorem says as long as you have that differentiable continuous function, that you're going to have that value c exists, and you can find it. So we are going to now try to illustrate it here. So the first thing that we would do for the mean value theorem is we would just say we want to make sure everything's valid so that we can use the mean value theorem. So f is continuous and differentiable on that 0 to 2 as it is a polynomial. And we know that polynomials are smooth and continuous on all real numbers. Then what we need is we need to think about what is the slope of that secant line. So slope of secant line. So we need f of 2 minus f of 0 over 2 minus 0. So this is finding the slope of the green line. So we plug that in, and you can pause if you want and come up with that slope, but f of 2 is, we can see we're going to get 9, and f of 0 is a negative 1, and then we have our 2 minus 0. So this is going to give us 5. And you can actually, arguably you can see that, that it's a nice slope there, but we need to do it this way because we don't always have the graph. So we get that the slope of that line is green. The slope of that green line is 5. And then what the mean value theorem tells us is there is some point c so that the slopes are the same. But on the function itself, the slope is the derivative. So if we take the derivative of our function, you can pause if you want, we get this. And so the MVT implies there is a C such that 3c squared plus 1 equals 5. And if we solve this for c, we get plus or minus, it looks like 2 over root 3, which is the same as 2 root 3 over 3. So yes, that there is always the possibility of having more than one C value. The mean value theorem basically says there's at least one here. So we know that our negative value would not be something that we would need on our interval from 0 to 2. And so we would say, so C is 2 root 3 over 3. And if you put that into your calculator, you're going to get 1.15 if you were asked for a decimal. And you can see that makes sense. We have the picture there. We can see that it's a little bit more than 1, pretty far from 2. And so we're not too surprised to find out that that is our C value. But that is a way to show that the MVT is valid and an example of how to find what that value is that you are told does exist. So a couple consequences of the mean value theorem, and I will prove the first one and then I'll show an example for number 2. But we have consequences of the MVT just means since the MVT is true, what kind of falls out from that? That's what it means to say consequences. What like comes out from it that helps us in maybe other ways. So we're told, number 1, if the derivative of a function is 0 for everything, all x in some interval, then that tells us that the function is a constant. Now you might say, well, of course, if the derivative is always 0, then it's a constant. But I mean, that has to be proved. You can't say, well, I can see it, and so it works. So to think about this, we're going to let x1 be less than x2 in our interval AB. Okay, so that just tells us that x1 is a smaller x value on the interval. So x1 is here, x2 is here. We don't know what they are, we just know that they're in the interval, and we know that x1 is a smaller value than x2. Now we're told, since f of x is differentiable, and we're told that because we're told that f prime of x equals 0. So that means that f prime of x exists and that it's 0. So that tells us that the function is differentiable. And I don't really need this, but it's differentiable on some interval AB, because we are told that. That means it is continuous. If it's differentiable, it's continuous. This is something we already have. And so it's differentiable, it's continuous on AB, thus on x1, x2, as well. So if it's continuous on the whole interval, it's going to be also continuous on the interval from x1 to x2, wherever that is inside. Okay. And I can even say that it's going to be including x1 and x2. All right, so now we know, thus, what the MVT tells us is thus there is a C on that interval, x1, x2, with, so this is the MVT, this is what the MVT tells us, because again, it's a consequence of the MVT, with, and then we're told f prime of C, okay, so the derivative at that value C must be equal to f of x2 minus f of x1, the secant line between the two values, x2 minus x1. That's what the MVT says. So we're using MVT here. Okay, but since and then we already were told here that the derivative is always 0, it tells us that at whatever value of c that occurs, then what has to be true, since f prime of x is 0 for everything, it tells us that this has to be true. And what I talked about in the video for section 3.1, I believe, is anytime you have a fraction equaling 0, that must imply that the numerator is equal to 0. It's the only time a fraction can be equals to 0. But of course, that tells us that f of x1 has to equal f of x2. Big idea here is x1 and x2 can be anything within that interval. And because of that, we're being told that the y values are the same. And again, the arbitrary x1, x2 tells us that since our y values are the same, thus f is a constant. Okay? So f must be a constant because we've shown that all the y values are the same. And we know that if all the y values are the same, then you have a constant. That's by definition. So we're done with that. And I'll just mention the second one, and then I'll show an example of it. So the next, number 2 here says, if the derivatives of two functions are the same for every single value on an interval. So it means the slope of the tangent line for both of those functions the same, every single point. It means that there is some constant c. Now notice c is not a value here within the function. So what this tells us is that the two functions only differ by a vertical shift. That could be up or down depending on if c is positive or negative. But that is the only difference that they can have between them. And I'm going to show you an example right now. So we have show that sine squared x equals negative cosine squared x plus 1. Now I was going to do the graphs of this, but of course you're showing that these two functions are equal, and so they are literally the same graph. There is no difference between them, because in this case you're showing that the two things are actually equal, not that one is just a shift from another. You're showing that these two sides are equal. So what we'll do is, and this is again just an example of one of the consequences of the mean value theorem, we'll let f of x equal sine squared x, and we'll let g of x equal negative cosine squared x plus 1. So we'll consider them both sides as their own separate functions. Now when you take the derivative of, and if you want, you can pause and take the derivative of both and then check your answer. So the derivative of sine squared, I need the chain rule. So I'm going to have 2 sine x and then the derivative of sine x, which is cosine x. Now, when I take the derivative of g of x, I'm going to have negative 2 cosine x, and then the derivative of cosine x is going to be a negative sine x. So notice this is, just simplifying this a little bit here, 2 cosine x sine x. The derivative of 1, of course, is 0, so it's gone. So we notice that the derivatives are the same. Okay, derivatives are the same. And so now the idea here is, let me write that. So f prime of x equals g prime of x. We just showed that. Okay, so this tells us that, what the consequence of the MVT, that number 2 there, it tells us that f of x has to equal g of x plus c for some c. Okay, so there's some value for which these two functions here should only differ by a constant. But we want to show that that constant is 0 because we are trying to say that these two functions are exactly the same. So for some c, but what c? Okay, so let's let x equal 0. So, because I mean, it's true for all values, so we'll put x equals 0. So f of 0 equals sine of 0 squared, and g of 0 equals negative, and then cosine of 0 squared plus 1. And so we are told that 0 must equal negative 1. Cosine of 0 is 1. Square that is 1. Negative 1 plus 1 plus c. I mean, that's the idea here. And because this is f of 0 and g of 0 plus c. And so that tells us that c equals 0. So we're done. Thus, we know that this function must be equal to this function for actually all x in R. And if you were to graph those in Desmos or something, you would see that they're the exact same function. Their derivatives are the same at every single point. One other thing we can do with the MVT is show that we can kind of bound functions depending on what we know by the MVT. So suppose you have a function that's differentiable on an interval, so you know as well that it's also continuous. You're given a value, f of 0 equals 2. So you're not told what the function is, you're just told that you have some y value, say for example right here, you're told that f of 0 equals 2, and you're talking about this interval up to 2. So you don't know where the function ends, but you are told that the derivative of the function is always less than or equal to 3. And that's an important piece of information because it essentially bounds the function by saying the slope of any point, that tangent line, can never be greater than 3. And, you know, if it could be anything, you could have tangent lines that do this and make, you know, that's a very steep tangent line. So it's kind of indicating something about your function in terms of what's happening to it on an interval. So it allows us to think about what would be the maximum value. So I mean, the function can do anything, we don't know, but by knowing that the slope of every single tangent line is less than or equal to 3, we are bounding it. So what we know is that because it's differentiable, the function is continuous, so the MVT is valid here. It tells us that if we think about the secant line, f of 2 minus f of 0, 2 minus 0. So I'm just thinking about the secant line from here to here. We know that that secant line and everything regarding that secant line, because we know the derivative, it's always less than or equal to 3, because we're told that the derivative is always less than or equal to 3. So if we think about, because again, our job here is to try to think about f of 2. That's why I'm using the secant line, because I'm being asked specifically about that y value. Notice we have basically an equation here, and we just want to solve this for f of 2. So if you want, you know, you're welcome to think about that. We can plug in, well, we know f of 0. We're not plugging anything in. F of 0 is 2. And then in our denominator, we have 2 minus 0, so I can multiply that, bring that over here. I have f of 2 minus 2 is less than or equal to 6. And then by adding, I get f of 2 is less than or equal to 8. Okay? So f of 2 will be less than or equal to 8 at 8. Equal to 8. There we go. And again, this is because what's happening here is you're bounding your derivative, and so that essentially bounds the slope of the tangent lines, which bounds how fast the function can increase. And so we're told that no matter what happens between 0 and 2, the f of 2, no matter what the function is with those requirements, f of 2 will always be less than or equal to 8. And that is section 3.2.